Hello, and welcome to Space for Sleep. In the winter of 1935, a disagreement about reality became sharp enough to be written into the language of physics. Albert Einstein, Boris Podolsky, and Nathan Rosen had been thinking about the new quantum mechanics, a theory that was astonishingly successful at predicting the behavior of atoms and light. They did not deny its success. Their objection was deeper. They believed the theory could not be the final description of nature because, in certain carefully prepared situations, it seemed to connect distant physical systems in a way that no ordinary picture of cause and effect could explain. Einstein later used a phrase that became famous: spooky action at a distance. The phrase is memorable, but it can also mislead. Quantum entanglement is not a ghostly force reaching across space. It is not a hidden beam between particles. It is not a method for sending messages faster than light. And the experiments that followed did not simply prove that Einstein was foolish while everyone else had understood the universe correctly. The real story is more interesting than that. Einstein helped expose the problem with extraordinary clarity. John Bell later discovered that part of the disagreement could be converted into mathematics. Experiments then showed that nature produces correlations stronger than an important class of local explanations allows. Those experiments are now among the most carefully tested demonstrations in modern physics. Yet even after the experiments succeed, a question remains. What kind of reality produces those correlations? That question is where entanglement begins. Imagine two ordinary coins placed in two boxes. One coin is heads up and the other tails up. The boxes are closed, mixed, and carried to opposite sides of a room. You open one box and see heads. At once you know that the other contains tails. Nothing mysterious happened at the second box when you looked into the first. The information was already fixed. Your uncertainty disappeared, but the distant coin did not need to change. This simple example captures a classical correlation. The two objects carry definite properties, even when an observer does not know them. The correlation can be explained by a common history. Entanglement is different. To understand how, it helps to begin before there are two particles at all. Quantum theory represents a physical system with a mathematical state. For a simple two-outcome experiment, the state can contain two possibilities at once. A photon may be prepared so that a measurement in one polarization basis can return one of two outcomes. An electron spin may be prepared so that a measurement along a chosen direction can return one of two values. The theory does not assign ordinary probabilities alone. It assigns probability amplitudes, quantities that can add, cancel, and interfere. That distinction is responsible for much of quantum behavior. If a classical coin is hidden beneath a cup, it is already heads or tails whether anyone looks. Uncertainty belongs to the observer. In quantum mechanics, a superposition generally cannot be treated as nothing more than ignorance about one concealed classical alternative. Interference experiments show that the amplitudes associated with alternatives can combine before a measurement produces one definite recorded result. It is tempting to say that a particle is literally in several classical states at once. That phrase is useful as a first image, but it is not exact enough to carry the whole subject. A quantum superposition is not simply a tiny object secretly occupying several ordinary realities in the everyday sense. It is a quantum state with components relative to a chosen basis, and different measurement bases reveal different structures within that state. The choice of basis matters. Take a photon. One laboratory may describe polarization using horizontal and vertical directions. Another may rotate the apparatus by 45 degrees and use diagonal directions. A state that is definite in one basis can be a superposition in another. There is no single list of classical properties that reproduces every possible measurement as though all answers had been written in advance on the photon. With one quantum system, this already challenges intuition. With two systems, something stronger becomes possible. Suppose a source creates two photons in a joint state constructed so that their polarization results are correlated. The state of the pair can be perfectly well defined even when quantum theory does not assign each photon its own independent pure state. The mathematical description cannot be factored into one complete state for photon A multiplied by another complete state for photon B. That inability to separate the joint state is the essential meaning of entanglement. The whole has a quantum description that cannot be reduced to separate descriptions of its parts. This point is more important than the popular picture of an invisible thread. Entanglement is not an extra force joining already independent particles. It is a property of the state of the combined system. A useful example involves two spin 1/2 particles prepared in a singlet state. If both spins are measured along the same direction, the outcomes are always opposite. If one detector reports one orientation, the other reports the opposite orientation. If that were the entire story, the glove box analogy might be enough. Perhaps one particle left the source carrying an instruction that's set up, while the other carried down. But the experimenters are not restricted to measuring along one direction. They can rotate their detectors. They can choose among different axes only after the particles have separated. And it is the pattern of correlations across many different choices that makes entanglement impossible to imitate with a broad class of local hidden instructions. A single pair does not reveal the pattern. Each local result is unpredictable. One observer sees a sequence that looks random. The distant observer also sees a sequence that looks random. Only after the two observers bring their records together through ordinary communication do the correlations appear. This is one of the most important facts in the subject. Entanglement creates correlations that outrun a classical local model, but it does not give either observer control over the random outcome. Without control, there is no message to encode. Without comparing the records later, neither side can use its local data to discover which measurement was performed far away. So the mystery is not that useful information visibly races across space. The mystery is that the joint statistics refuse to behave as though distant outcomes were generated by local pre-existing answers. That is subtler and stranger. The historical path toward this realization began with a problem about completeness. In 1935, Einstein, Podolsky, and Rosen published a paper asking whether the quantum mechanical description of physical reality could be considered complete. Their argument used an entangled state with continuous quantities rather than the spin examples common today, but the logic was similar. They began with a criterion for what they called an element of physical reality. Roughly, if one could predict the value of a physical quantity with certainty without disturbing the system, they argued that there should be something in reality corresponding to that value. Entanglement allowed a disturbing conclusion. By choosing what to measure on one member of a distant pair, an experimenter could predict with certainty the corresponding result for the other member. If the distant particle could not be physically disturbed instantaneously by that choice, then the predicted quantities seemed to belong to it already. Yet quantum mechanics did not assign simultaneous definite values to all of those incompatible observables. Einstein and his colleagues concluded that the quantum description was incomplete. The paper did not present the modern experimental hidden variable model often attributed to it. Its central claim was that either the quantum state failed to capture all elements of reality, or one had to accept a deeply unfamiliar relation between separated systems. Erwin Schrödinger immediately recognized how fundamental this situation was. In the same year, he introduced the word entanglement and described it not as one odd side effect of quantum mechanics, but as its characteristic feature. That judgment has aged remarkably well. For decades, however, the debate seemed difficult to settle. Different interpretations could agree on the outcomes of ordinary experiments. One physicist could say that the wave function was complete. Another could imagine deeper variables beneath it. If both pictures predicted the same numbers, the disagreement looked philosophical rather than experimental. Then John Bell found the crack. Bell was born in Belfast and worked for much of his career at CERN. He was deeply interested in the foundations of quantum theory, but he was not satisfied with vague statements that hidden variables had already been ruled out. In particular, the work of David Bohm had shown that a deterministic hidden variable theory could reproduce quantum predictions, provided it was explicitly non-local. So Bell asked a sharper question. Could a theory keep both hidden variables and a strong form of locality? Could measurement outcomes be explained by information carried from the common source, with the result at one detector unaffected by which setting was chosen at a sufficiently distant detector? In 1964, Bell showed that such theories cannot reproduce every prediction of quantum mechanics. This was an extraordinary result because it created an experimental boundary. Consider a source producing pairs. Far apart, two observers choose between different detector settings. Call them Alice and Bob. On every trial, Alice records one of two possible outcomes. Bob records one of two possible outcomes. Suppose the pair left the source carrying hidden information that determines, perhaps probabilistically, how each particle should respond to every possible local setting. Suppose also that Alice's outcome cannot depend on Bob's last moment setting when they are separated, so that no ordinary light speed influence could connect the events. Under a family of assumptions of this kind, the correlations among all the possible setting combinations are constrained. Bell inequalities express that constraint. Quantum mechanics predicts entangled states that violate it. The exact mathematics can be written in several forms. One commonly used version is the CHSH inequality, named after John Clauser, Michael Horn, Abner Shimoni, and Richard Holt. It combines correlations from four pairs of measurement settings. Local hidden variable models are bounded by a particular value. Quantum mechanics can exceed that bound, though it still respects a separate quantum limit. The beauty of the inequality is that it does not require an experimenter to know the hidden variables. It says that if outcomes arise from that broad local structure, the observed statistics must fall inside a certain region. Nature can therefore answer. And nature answered. In 1972, Stuart Friedman and John Clauser performed an influential test with pairs of photons emitted by calcium atoms. Their results agreed with quantum mechanics and violated the relevant Bell inequality. The experiment was impressive, but foundational experiments invite difficult questions. Were all the particles detected? Could the detected sample have been biased? Could information about one detector's setting somehow reach the other side before the result was registered? Could the source have known the settings in advance? These possibilities became known through various loopholes. A loophole does not mean that physicists believed a conspiratorial classical mechanism was probably hiding in the apparatus. It means that if the goal is to rule out a logical family of explanations, the experiment should avoid silently assuming the conclusion. Alain Aspect and colleagues made major advances in the early 1980s. One celebrated experiment changed measurement settings rapidly while photons were already in flight, making a simple subliminal coordination mechanism increasingly implausible. Technology continued improving. Detectors became more efficient. Random setting choices became faster. Separation distances increased. Atomic systems and solid-state spins joined photons as platforms for Bell tests. In 2015, several groups reported experiments designed to close the major detection and locality loopholes at the same time. One widely discussed experiment led by Ronald Hansen used electron spins associated with defects in diamond at laboratories separated by about 1.3 kilometers. Other experiments used high-efficiency photon detection. The statistics differed in strength from experiment to experiment, but the broader result was consistent. Bell inequalities were violated under conditions that eliminated the standard experimental escape routes. In later tests, researchers pushed on another assumption: the independence of measurement choices from the hidden variables describing the source. One approach used human choices. Another used light arriving from distant astronomical sources to help choose detector settings, pushing any hypothetical common cause correlating the source with those settings farther into the past. These experiments do not prove that every logically imaginable loophole is impossible. No finite experiment can do that. A superdeterministic model, for example, denies the independence between measurement choices and hidden variables at a fundamental level. Retrocausal approaches explore whether future measurement settings can enter the explanatory structure without ordinary backward-in-time signaling. Non-local hidden variable theories, such as Bohmian mechanics, give up Bell locality explicitly. Bell's theorem is powerful precisely because its conclusion is more careful than the slogan that all hidden variables are dead. Local hidden variable explanations satisfying the relevant independence assumptions cannot reproduce the observed correlations. That is what the experiments establish. It is enough to overturn a very natural classical picture. It is not enough to dictate one unique metaphysics. In 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The award marked an unusual transformation. A question once treated as almost too philosophical for the laboratory had become the foundation of an experimental technology. But before following that technology, one misconception has to be removed completely. Entanglement does not allow faster-than-light communication. Imagine Alice and Bob again, separated by a great distance. They share many entangled pairs. Alice wants to send Bob a 1-bit message instantly. Perhaps she hopes to choose a measurement that forces Bob's particle into one detectable condition for 0 and another for 1. Quantum mechanics does not let her do this. Alice can choose what observable to measure, but she cannot choose the individual result. Bob's local sequence remains random. If Alice changes her measurement basis, Bob cannot discover that change by examining his results alone. His local statistical distribution is unchanged. Only when Alice later sends information about her settings and outcomes through a normal classical channel can Bob sort the records and reveal the quantum correlations. That classical message cannot outrun light. The structure is therefore deeply non-classical without functioning as a superluminal telegraph. This point also resolves a common mistake in the language of instantaneous collapse. Some interpretations describe measurement as a collapse of the quantum state. If the entangled state is spread across distant systems, the mathematical state update can be written as occurring across the pair when a result is known. But a collapse in the mathematical description is not itself an observable flash moving from Alice to Bob. Different interpretations do not even agree that a physical collapse occurs. And relativity gives no universal meaning to two distant space-like separated events being simultaneous. Observers moving relative to one another can disagree about which measurement happened first. Experiments are constructed so that neither event lies inside the other's light cone. The correlations do not pick out a preferred order that can be observed and used to transmit information. This is why the sentence that one particle responds instantly in every reference frame should be avoided. The data show correlations between space-like, separated measurements. They do not show a visible message, force, or measurable causal pulse racing between the apparatuses. That distinction is not an attempt to make entanglement less strange. It identifies where the strangeness actually lives. Once the no-signaling boundary is clear, the interpretational problem becomes easier to state and harder to solve. Quantum mechanics provides a remarkably precise algorithm for predicting experimental statistics. Prepare a state. Allow it to evolve. Choose a measurement. Calculate the probabilities. Compare the results with data. The procedure works. What remains disputed is what the mathematical ingredients represent. Does the wave function describe a physical object? Does it describe information? Does measurement create an outcome, reveal one branch, update an observer's description, or mark an interaction in a larger relational network? Entanglement makes these questions impossible to ignore because the state of the whole system can be definite, while the subsystems do not possess separate pure state descriptions. The family of views often called Copenhagen interpretations refuses to turn the quantum formalism into a hidden classical movie. There was never one single Copenhagen doctrine shared word for word by Niels Bohr, Werner Heisenberg, and everyone around them. The label covers several related attitudes. A common theme is that measurement outcomes are the events physics is organized to predict, while asking for a classical set of definite properties existing independently of every measurement context may be asking the wrong question. Bohr placed great emphasis on experimental arrangements. A quantum property is not always something that can be discussed independently of the procedure used to define and measure it. Position, momentum, polarization, and spin components belong to different experimental contexts. Complementary arrangements reveal different aspects that cannot all be combined into one classical picture. Entanglement deepens that contextuality. The quantum state belongs to the pair, and the predictions concern relationships among possible outcomes. One can use collapse language here, but caution matters. In textbook calculations, once an outcome is registered, the state used to predict later measurements is updated. Whether that update is a literal physical process is not settled by the calculation itself. Many worlds takes a very different route. Hugh Everett proposed in the 1950s that the quantum state never collapses. The universal wave function always follows its ordinary deterministic quantum evolution. Measurement is simply a physical interaction that entangles the apparatus, the observer, and the measured system. Suppose Alice measures one member of an entangled pair. In an Everettian description, there is no single physical event that deletes all but one outcome. Instead, the combined state develops branches in which different records exist. Within one branch, Alice has recorded one result. Within another, she has recorded the alternative. When Bob later measures, the branching structure preserves the correlations required by the original entangled state. This picture avoids a special collapse rule. It also changes the question. Instead of asking how a distant particle instantly acquires a value, the interpretation asks how observers inside an evolving universal state experience definite records associated with branches. The price is substantial. One must take the branching quantum state seriously as reality. Exactly how branches should be defined, why probabilities obey the familiar Born rule, and what it means to count possibilities remain subjects of philosophical and technical discussion. Bohmian mechanics chooses almost the opposite direction. Particles have definite positions. A wave function guides their motion. The theory is deterministic once the relevant initial configuration is specified, but it is openly non-local. For an entangled many-particle system, the guiding structure is defined on configuration space, and the velocity of one particle can depend on the configuration of distant particles. Bell regarded Bohm's theory as an important demonstration because it showed that hidden variables were not impossible in general. What had to be sacrificed was the kind of locality Einstein hoped to preserve. Bohmian mechanics reproduces the standard statistical predictions when its initial configurations are distributed in the appropriate quantum equilibrium. It therefore does not evade Bell experiments by satisfying Bell inequalities. It reproduces their violation through an explicitly non-local theory. Other interpretations shift emphasis again. Relational quantum mechanics treats properties as meaningful relative to interactions between systems rather than as a single observer-independent catalog of values. Cubist approaches treat the quantum state as encoding an agent's expectations for future experience and interpret probability updating in explicitly informational terms. Objective collapse theories go in another direction, modifying ordinary quantum dynamics so that superpositions really do collapse spontaneously under certain conditions. Unlike interpretations that reproduce standard quantum mechanics exactly, objective collapse models can in principle lead to experimentally different predictions, making them physical theories rather than only alternative readings of the same equations. There are also retrocausal proposals, consistent histories approaches, modal interpretations, and others. The existence of so many options can sound as if physics has failed to understand its own theory. That would be unfair. Physicists understand extraordinarily well how to calculate with quantum mechanics and how to test its predictions. The interpretational debate concerns what underlying picture, if any, should be attached to a formalism whose predictions are already secure across an enormous range of experiments. The disagreement is especially persistent because many interpretations are designed to reproduce the same observable results. If two descriptions assign different stories to what happens between measurements, but always predict the same recorded outcomes, ordinary experiments cannot choose between them. Bell's theorem did not end interpretation. It changed the space of possible interpretations. Any satisfactory account has to reproduce Bell, violating correlations while preserving the observed impossibility of controllable faster than light signaling. That combination is the central constraint. It is worth slowing down over how strange that combination is. Alice's outcomes are random. Bob's outcomes are random. Their choices can be made at the last moment. When the records are compared, the correlations exceed what local hidden instructions can provide. Neither side can exploit the effect to send a message. The world gives more joint structure than either observer can access locally. Entanglement lives in the relationship. That sentence sounds philosophical, but it can be made mathematical. Take a pure entangled state of two subsystems. The state of the whole can have zero quantum uncertainty in the sense that it is represented by one definite vector. Yet if one subsystem is considered alone, its reduced state is mixed. Locally, it behaves as though there is uncertainty. Information about the whole is not stored as information possessed separately by each part. Some of it exists only in correlations. This idea is now central to quantum information theory. A classical message can be copied freely. A quantum state cannot, in general, be perfectly copied if it is unknown. This is the no-cloning theorem. Classical correlations can often be understood as shared lists of values. Quantum entanglement can be consumed as a resource for tasks that no shared classical randomness can reproduce with the same capabilities. The change in language is revealing. Early debates asked whether entanglement exposed an embarrassing incompleteness in quantum theory. Modern laboratories speak of creating entanglement, distributing entanglement, purifying entanglement, measuring entanglement, and spending it. What once looked like a philosophical nuisance became an engineering resource. To see how, imagine a laboratory producing pairs of photons. A laser enters a nonlinear crystal. Under suitable conditions, one photon from the pump can give rise to two lower energy photons whose properties are correlated by conservation laws and by the quantum interaction. The resulting pair can be prepared in an entangled polarization state. The photons may leave in different directions. Waveplates rotate their polarization bases. Single photon detectors register arrival events. Electronics record timestamps. After thousands or millions of repetitions, correlation functions emerge. Nothing about the apparatus looks metaphysical. There are cables, lenses, crystals, detectors, clocks, vacuum systems, and computers. Yet the statistics cannot be generated by the local classical picture Bell constraint. Entanglement can also be created between trapped ions. Two charged atoms are confined by electromagnetic fields in a vacuum. Laser pulses manipulate internal energy levels and collective motion. Operations link the quantum states of the ions so that the pair becomes entangled. Superconducting circuits create entanglement in a completely different physical object. Here the qubits are engineered electrical systems cooled to temperatures near absolute zero. Microwave pulses control quantum states involving currents and charges spread across circuits large enough to see under a microscope. Couplers allow neighboring circuits to undergo 2-qubit gates that produce entanglement. Neutral atoms can be held in optical tweezers. Rydberg interactions can produce strong conditional behavior between them. Nitrogen vacancy centers in diamond provide localized electronic spins that can be manipulated optically and coupled to photons. Quantum dots, defects in silicon, photonic chips, atomic ensembles, and other systems all support forms of entanglement. This diversity matters. Entanglement is not a peculiar property of one exotic particle. It is a structural feature of quantum states. The challenge is not creating it in principle. The challenge is controlling it before the environment becomes entangled too. That process is called decoherence. A fragile quantum system rarely remains isolated. A photon scatters. A vibrating lattice interacts with a qubit. Thermal radiation carries away information. An uncontrolled electromagnetic field shifts a phase. The system becomes correlated with degrees of freedom that the experimenter does not track. From the perspective of the small subsystem, interference becomes suppressed. This is sometimes described as entanglement disappearing. More accurately, the carefully controlled entanglement has often spread into a much larger system plus environment state. The correlations have become inaccessible for the intended experiment. Decoherence helps explain why everyday objects do not display obvious quantum superpositions. A dust grain in air is bombarded by molecules and photons so frequently that phase relationships associated with macroscopically different alternatives become encoded in the environment almost immediately. The surrounding world is continually monitoring the object in a loose physical sense. This does not, by itself, solve every version of the measurement problem. It does explain why interference between macroscopic alternatives becomes extraordinarily difficult to observe and why classical looking records are stable. Entanglement therefore plays two opposite roles. Controlled entanglement is the resource quantum technologies seek. Uncontrolled entanglement with the environment is one of the main ways those technologies lose coherence. Building a quantum device is partly the art of deciding which correlations are allowed to grow and which must be prevented. That art becomes especially beautiful in quantum teleportation. The name sounds more dramatic than the process. No object disappears from one location and appears at another. No person is copied. No matter travels instantaneously. What can be transferred is an unknown quantum state. Suppose Alice has a qubit in a state she does not know. Alice and Bob also share an entangled pair, with one member held by Alice and the other by Bob. Alice performs a joint measurement on her unknown qubit and her half of the entangled pair. The result is one of several possible classical outcomes. That measurement changes the relationship among the systems. Bob's qubit is now related to the original unknown state, but Bob cannot yet recover it. Alice must send him the classical measurement result. For the standard qubit teleportation protocol, 2 classical bits are sufficient. When those bits arrive no faster than light, Bob performs the corresponding operation on his qubit. The state he holds becomes the original unknown state. The initial state at Alice's location no longer exists as a second copy. The no-cloning theorem is respected. Relativity is respected. Entanglement has supplied a resource that changes what the classical message can accomplish. Quantum teleportation was proposed theoretically in 1993 and demonstrated experimentally a few years later. It has since become a routine primitive in quantum information experiments across many physical platforms. Its importance extends beyond the striking name. Teleportation allows quantum information to be moved without physically transporting the original carrier through every part of a device. In fault-tolerant architectures, teleportation-like circuits can implement gates and move logical information. In networks, teleportation provides a way to transfer states once entanglement has been distributed between nodes. That leads to another idea, entanglement swapping. Imagine Alice entangled with an intermediate station, and that station independently entangled with Bob. At first, Alice and Bob have never shared an entangled pair directly. A suitable joint measurement at the middle station can project the outer systems into an entangled state. After the relevant classical information is communicated, Alice and Bob possess correlations even though the particles they hold never interacted with each other. This is entanglement swapping. It sounds like the connection has leapt across the middle. Again, nothing useful outruns light. The entangled relationship is established conditionally, and classical communication is required to know how to use the resulting state. Entanglement swapping is a basic ingredient in proposed quantum repeaters. Ordinary optical signals can be amplified along a fiber network because classical information can be measured and regenerated. Unknown quantum states cannot simply be measured, copied, and resent without disturbance. A quantum repeater instead aims to create entanglement across shorter links, store it in quantum memories, improve its fidelity when necessary, and connect the links through swapping until distant network nodes share high-quality entanglement. That is difficult. Photons are lost in fiber. Memories decohere. Entangling operations fail with non-zero probability. Timing must be synchronized. Errors accumulate. But the architecture suggests what a future quantum internet would actually be. It would not be an internet where messages move instantaneously. It would be a network capable of distributing entangled states as an additional resource alongside classical communication. Such a network could enable distributed quantum computing, improved clock synchronization protocols, networked sensors, secure communication tasks, and tests of fundamental physics across large distances. The strange connection would become infrastructure. The most mature communication application built from quantum principles is quantum key distribution. Its purpose is not to send a secret message directly through entanglement. Its purpose is to establish a shared random key while making certain forms of eavesdropping detectable. Classical cryptography often protects data because a mathematical problem is believed to be difficult for an attacker to solve with available computing power. Quantum key distribution aims for a different kind of guarantee. Under the assumptions of a specific protocol and implementation, security can be tied to the laws of quantum physics. That statement needs the same care as every other statement in this subject. A slogan sometimes says that any eavesdropper must measure the quantum signal. Every measurement disturbs it, and therefore eavesdropping is automatically detected. Real systems are more complicated. Not every quantum measurement produces an obvious disturbance in every protocol. Practical devices have imperfections. Sources emit unwanted signals. Detectors have vulnerabilities. Side channels can leak information. Security proofs therefore specify exactly what devices and adversaries are assumed. Some quantum key distribution protocols do not even require entanglement as an operational ingredient in the simple way a Bell experiment does. Others can be understood through equivalent entanglement-based pictures. A particularly ambitious form, device-independent quantum key distribution, does make Bell inequality violation central. If two distant devices generate correlations strong enough to violate a Bell inequality under suitable conditions, the users can certify aspects of secrecy without trusting a detailed internal model of the devices. The Bell violation itself becomes evidence that the outputs contain private randomness not generated by a local predetermined strategy. This is conceptually extraordinary. The same inequality that was invented to test the philosophical structure of quantum mechanics becomes a tool for cryptographic certification. Yet device-independent systems are experimentally demanding. They require high-quality entanglement, efficient detection, low loss, and carefully closed loopholes. Proof of principle demonstrations exist, but deploying such systems broadly is much harder than demonstrating ordinary quantum key distribution. Entanglement has also been distributed over remarkable distances. Photons have been sent through optical fiber and free space. Satellite experiments have distributed entangled photons between ground stations separated by large distances. The Mischief satellite helped demonstrate satellite-based entanglement distribution and quantum communication over scales that would be extremely difficult through fiber alone, because optical loss grows rapidly with distance. Again, the satellite does not create a faster-than-light channel. It helps distant laboratories share quantum states. The classical steps of the protocols remain limited by ordinary causal structure. The engineering achievement is not speed beyond relativity. It is preserving delicate correlations while photons cross atmosphere, vacuum, telescopes, optics, and detectors. The same lesson appears inside a quantum computer. Popular descriptions often say that a classical bit is 0 or 1 while a qubit is 0 and 1 at the same time. So a quantum computer tries all answers simultaneously. That language captures a fragment of the idea and hides most of the difficulty. A register of qubits can indeed occupy a state described by amplitudes over many computational basis strings. For n-ideal qubits, the general pure state requires amplitudes associated with 2 to the power n basis states. But a quantum computer cannot simply read all those amplitudes at the end. Measurement returns a limited classical result. A useful quantum algorithm must arrange interference so that amplitudes associated with helpful outcomes are enhanced while others are suppressed, or must estimate some global property without reconstructing the entire state. Entanglement is often crucial to this process because it allows the register to occupy states that cannot be written as independent states of each qubit. But entanglement alone is not a magic measure of computational power. Some highly entangled quantum states can be simulated efficiently for particular structures. Some quantum protocols gain advantages from resources described more precisely by contextuality, interference, magic states, or other forms of non-classicality. The relationship between entanglement and quantum advantage is rich rather than one-dimensional. Still, entangling gates are indispensable in general-purpose quantum computation. A machine that could manipulate only isolated qubits would be severely limited. 2-qubit operations allow information to become distributed across the register in ways that support quantum algorithms and quantum error-correcting codes. One famous algorithm is Shor's factoring algorithm. A sufficiently large fault-tolerant quantum computer could use it to factor large integers far more efficiently than known classical methods, threatening widely deployed public key systems such as RSA and related schemes whose security depends on mathematical problems that quantum algorithms can attack. That does not mean today's quantum computers can break ordinary internet encryption at scale. They cannot. The gap between a laboratory processor and the fault-tolerant machine required for cryptographically relevant factoring remains enormous. Nevertheless, governments and standards bodies have already moved toward post-quantum cryptography because encrypted data can remain valuable for years and because infrastructure transitions take time. Another application is more native to the physics itself. simulating quantum systems. Molecules, magnetic materials, superconductors, and chemical reactions are quantum systems. Their many body states can become entangled, and the classical resources needed for exact simulation often grow rapidly with system size. A controllable quantum processor may represent those states more naturally. The hope is not that every chemistry problem becomes easy. It is that selected problems in electronic structure, dynamics, materials, and strongly correlated matter may eventually be handled in regimes where classical approximations become inadequate. The word eventually matters. Current hardware is noisy. A qubit does not sit forever in an ideal state. Control pulses have errors. Measurements fail occasionally. Interactions with neighboring hardware cause unwanted correlations. Energy relaxation and dephasing erase information. The central engineering problem is quantum error correction. At first, this sounds impossible. If measuring an unknown quantum state disturbs it, and if unknown quantum states cannot be copied perfectly, how can an error be detected and corrected without learning and destroying the encoded information? The solution uses entanglement again. A logical qubit is encoded non-locally across many physical qubits. The information is stored in collective relationships rather than in one device. Additional measurements called syndrome measurements reveal information about errors without revealing the logical quantum state itself. One does not ask, what is the logical qubit's value? One asks, has a pattern characteristic of a bit flip, phase flip, or related error occurred? From repeated syndromes, a classical decoder infers likely errors and the control system compensates for them. This is one of the most elegant reversals in quantum technology. Entanglement makes quantum information fragile because the environment can steal correlations. Entanglement also allows that information to be spread across many physical systems so that local errors can be diagnosed without exposing the logical state. For decades, the key concept has been a threshold. If the physical components are too noisy, adding more qubits only adds more failure opportunities. If physical errors can be pushed below a code-dependent threshold, increasing the size of the error-correcting code can reduce the logical error rate. Recent experiments have reached important milestones in this direction. A widely discussed surface code experiment on Google's Willow processors demonstrated below-threshold quantum memory. When the code distance was increased, the logical error rate fell rather than rose, and the larger logical memory survived longer than its best constituent physical qubit under the reported conditions. This was not a complete fault-tolerant quantum computer. The demonstrated logical error rates were still far above those needed for many large algorithms, and scaling the code toward useful computation would require many more physical qubits, stable operations, fast classical decoding, and control of rare correlated errors. But the result was important because error correction behaved in the direction the theory requires. The engineering frontier has therefore moved. The question is no longer merely whether quantum error correction can exist in a textbook. The question is whether large systems can maintain below-threshold behavior while executing long, complex, fault-tolerant computations at economically and physically realistic scales. Entanglement is woven through that challenge. A surface code is not protected because each qubit becomes more isolated. It is protected because information is encoded into a carefully designed pattern of many-body quantum correlations, while repeated measurements reveal where the pattern has been damaged. This leads to an unexpectedly broad idea. Entanglement is not merely a strange connection between two particles. In modern physics, it is a language for describing how information is distributed across many body systems. That broader view takes us from quantum computers back into ordinary matter. Consider a magnet cooled near a quantum phase transition. In classical physics, phases of matter are often described by local order. Water freezes because molecules organize into a crystal. A ferromagnet develops a direction of magnetization. Quantum many-body systems can possess order that is more subtle. Ground states may contain long-range patterns of entanglement. Topological phases can store information in global properties that are insensitive to many local disturbances. Quantum spin liquids can avoid conventional magnetic order while supporting highly entangled states with exotic collective excitations. Entanglement entropy helps quantify this structure. Take a large quantum system and divide it into region A and the rest. Even if the entire system is in a pure state, region A can look mixed because it is entangled with its complement. A mathematical entropy constructed from the reduced state measures, in a precise sense, how much entanglement crosses the boundary for a pure bipartite state. The scaling of this entropy contains physical information. In many low-energy states of local systems, entanglement grows roughly with the boundary area rather than the volume of the region. At certain critical points, logarithmic corrections or other scaling behavior can reveal universal structure. In topological phases, subleading terms can encode topological information. These are not philosophical decorations. They help classify phases, design numerical methods, and understand when a many-body wave function can be approximated efficiently. Tensor network methods exploit limited entanglement structure to represent some quantum states without storing every amplitude of the full exponentially large Hilbert space. This is one reason the statement that a quantum computer simply holds exponentially many classical answers is too crude. Classical simulation difficulty depends not only on the number of basis states that could appear in a mathematical expansion, but on the structure of correlations among them. A system with modest entanglement may have a compact description. A system with certain complicated patterns may resist such compression. Entanglement therefore sits at the intersection of foundational physics and practical computation. It tells us why local pieces can fail to contain the information of the whole. It tells us why some quantum states are difficult to simulate. It tells us how error-correcting codes can hide logical information from local damage. And it gives us a measure with which to study phases of matter that cannot be understood through classical order parameters alone. This is far beyond the original image of two separated particles. Yet the image remains useful because it isolates the central fact. The world can possess joint properties that are not reducible to a collection of independent local properties fixed in advance. There is another way to feel Bell's result without beginning from an inequality. Imagine a game played by two separated boxes. Before each round, one of several possible questions is sent to each box. The boxes must answer with simple binary outputs. Before the game begins, they are allowed to agree on any strategy they like. Once a round starts, they cannot communicate. If the boxes are ordinary classical machines, even if they share an enormous file of synchronized random numbers, there is a maximum average success rate for certain versions of the game. The limit comes from logical consistency. A pre-written table of answers that succeeds for one combination of questions must fail often enough for another combination. Now replace the boxes with quantum devices sharing entanglement. With appropriately chosen measurements, they can win more often than the best local classical strategy permits. They still do not win every round. They still cannot exchange messages. But their statistics cross the classical boundary. This perspective turns Bell inequality violation into a task. It also shows why shared classical randomness is not enough. The boxes may carry identical random seeds, matching clocks, or arbitrarily complicated local programs. If their outputs are governed by a local strategy independent of the later question choices, the Bell limit remains. Entanglement supplies a different resource. This game-like picture is central to device-independent quantum information. Suppose a laboratory buys two mysterious black boxes from an untrusted manufacturer. The boxes claim to produce random numbers. How could the laboratory know that a secret file inside them is not simply replaying a predetermined sequence? If the boxes are sufficiently isolated from one another during each trial and produce a loophole-free Bell violation, the statistics cannot arise from a local predetermined list under the standard assumptions. The violation can certify genuine quantum randomness. Randomness, an idea that once looked like an embarrassment in Einstein's debate with quantum mechanics, becomes something that can be tested and harvested. This makes the question of randomness itself more subtle. Quantum theory predicts probabilities. In textbook language, a measurement on a suitable state produces intrinsically random outcomes. A deterministic Bohmian account instead attributes those statistics to unknown initial configurations while retaining non-local dynamics. Many worlds retains deterministic wave function evolution, but explains experienced uncertainty through branching. Operationally, however, Bell experiments can certify that the outputs are not explainable by local predetermined variables correlated with the measured system in the ordinary way. The laboratory can extract bits whose unpredictability is grounded in observed quantum correlations rather than merely in the complexity of a classical algorithm. This is a striking reversal of values. Classical engineering often treats randomness as noise. Quantum information can treat certain randomness as a resource. The same reversal appears in measurement. In classical science, measurement ideally reveals a property without changing it. A thermometer may disturb a small system slightly, but in principle one can imagine reducing the disturbance toward zero. Quantum measurements do not fit that simple picture. The outcome statistics depend on the relation between state and measurement basis, and incompatible measurements cannot all be treated as passively reading pre-existing values. Bell's theorem adds distance to the problem. Cauchy-Specker-type contextuality theorems, developed in another branch of quantum foundations, show that even without spatial separation there are severe limits on assigning non-contextual pre-existing values to all quantum observables while preserving the theory's predictions. Entanglement is therefore part of a larger break between quantum theory and classical realism. The break is not that objects become magical. It is that the classical idea of a complete hidden catalog of properties, independent of how they are measured and connected, cannot be carried unchanged into quantum physics. This can be seen in a simpler experiment with a single photon. A photon prepared with vertical polarization passes through a vertical polarizer with certainty in an ideal setup. Rotate the polarizer 90 degrees, and it is blocked. Place a polarizer at 45 degrees, and the transmission becomes probabilistic according to the quantum rule. Now add another polarizer behind it. The first measurement changes which state is relevant for the next one. This does not by itself prove entanglement, but it trains the intuition needed to understand why measurement settings matter. With entangled photons, both sides can choose settings, and the joint probability table contains the signature Bell isolated. The signature is statistical. No individual pair arrives with a label saying non-local. A single coincidence count proves nothing. The experiment requires many trials, careful calibration, random setting choices, timing analysis, detector characterization, and statistical tests. This is why the phrase quantum weirdness can be both useful and dangerous. It captures the emotional reaction. It can hide the extraordinary discipline of the evidence. A Bell experiment is not a magician showing two synchronized lights. It is a quantitative test of a precisely defined class of models. The correlations must have the right strength across the right choices. The stations must be arranged so that causal communication during the relevant interval is excluded under relativity. The setting generation must be characterized. Detection efficiencies must be high enough to avoid a biased subset. Statistical significance must be evaluated without pretending that every trial is independent if the apparatus has memory. Modern tests are sophisticated partly because physicists spent decades imagining how an apparent violation might be faked. The effort resembles a legal case in which every alternative explanation is invited to cross-examine the evidence. This also explains why the 2015 loophole-free experiments mattered even though earlier generations of physicists were already convinced quantum mechanics would win. Closing a loophole is not always about changing the most probable conclusion. Sometimes it is about turning an inference into a cleaner theorem about the physical world. The locality loophole asks whether information could travel between the measurement stations during a trial. The detection loophole asks whether the recorded events could be an unrepresentative subset, selected in a hidden variable-friendly way. The freedom of choice or measurement independence issue asks whether the variables describing the emitted system could be correlated with the variables choosing the detector settings. Experiments can push these possibilities into increasingly implausible corners. They cannot force someone to accept assumptions that person denies as a matter of fundamental theory. This is where superdeterminism enters. In a superdeterministic theory, the measurement choices are not statistically independent of the hidden variables associated with the particles. The random number generator, the experimenter's decision, the source, and perhaps events in their common past are correlated in just the right way to reproduce the observed Bell violations without the usual non-local structure. The word sometimes sounds like a conspiracy, but serious researchers have explored whether such models can be formulated naturally. The challenge is not merely philosophical discomfort. A useful theory must explain why these correlations take the quantum form, reproduce the broad success of quantum mechanics, and make new testable predictions rather than simply arranging every experiment to come out correctly after the fact. Retrocausal ideas take a different route. They question whether the direction of explanation must always run from past hidden conditions to future measurement results in the familiar classical way. If future measurement settings are allowed to constrain past variables in a time-symmetric framework, Bell correlations may be represented without a simple faster-than-light influence moving across space. Again, this does not mean messages can be sent into the past. A retrocausal interpretation must recover ordinary causal experience and no signaling statistics. These approaches remain minority research programs, but they are reminders that Bell's theorem is a precision instrument. It tells us which combination of assumptions cannot all survive. It does not print one preferred ontology at the bottom of the data sheet. Einstein's principle of locality was not an arbitrary prejudice. It grew from relativity. Special relativity says that space-time has a causal structure. Light cones separate events that can influence one another through signals moving at or below the speed of light from events that are space-like separated. For space-like separated events, there is no observer-independent answer to which happened first. One inertial observer may say Alice measured first. Another may say Bob measured first. If an explanation requires a detectable physical influence to leave whichever detector was first and reach the other instantaneously, it risks selecting a hidden preferred frame. Standard quantum theory avoids observable conflict with relativity because the predictions obey no signaling. The correlations exist without allowing either observer to control a superluminal transmission. Relativistic quantum field theory pushes this compatibility further. Fields are the fundamental objects, and observables associated with space-like, separated regions obey commutation relations that prevent one local operation from changing the outcome statistics available to a distant observer in a way that enables signaling. Entanglement is abundant in quantum fields. Even the vacuum state is not simply a product of independent states assigned to every spatial region. Nearby regions possess quantum correlations. This is one reason attempts to understand entanglement in field theory quickly meet deep ideas about locality, boundaries, entropy, and gravity. But before gravity enters the story, the vacuum itself deserves attention. Empty space in quantum field theory is not a classical nothing. It is the lowest energy state of interacting or free quantum fields, and its correlations extend across regions of space. If one divides space into two parts and asks for the quantum state of only one part, the answer generally reflects entanglement with degrees of freedom on the other side of the boundary. This entanglement is mathematically subtle. In continuum field theories, naive entanglement entropy can diverge because arbitrarily short distance modes contribute near the boundary. Physical cutoffs, renormalized quantities, and related constructions are used to extract meaningful information. The divergence is not a sign that entanglement is fake. It reveals how strongly quantum field theory ties neighboring spatial scales together. The boundary dependence becomes important in one of the strangest meetings in theoretical physics, the meeting of entanglement and black holes. Black holes forced physicists to ask where information goes when gravity becomes extreme. Classically, a black hole is defined by an event horizon, a boundary beyond which signals cannot return to the outside universe. Quantum field theory on a curved spacetime adds Hawking radiation. A black hole can radiate and, over an unimaginably long time, lose mass. This creates the information problem. If the black hole evaporates completely and the outgoing radiation is exactly thermal, what happens to the detailed quantum information in the matter that formed the black hole and later fell inside? Ordinary quantum evolution preserves information in a precise mathematical sense called unitarity. A pure quantum state evolves into another pure state. Complete destruction of information would require a profound modification of quantum mechanics. Entanglement stands at the center of the puzzle. In simplified descriptions of Hawking radiation, outgoing quanta are entangled with partners associated with the interior. As radiation accumulates, the entanglement structure raises a conflict between semi-classical gravity, quantum unitarity, and the smooth horizon expected from general relativity. The details have led to decades of work. Black hole complementarity, the Page curve, holography, firewall arguments, replica wormholes, quantum extremal surfaces, and other ideas. A full explanation would take us far beyond two entangled photons in a laboratory, but the connection is worth noticing. The same mathematical concept that tests local realism in a Bell experiment also measures how quantum information may be distributed across a horizon. One of the deepest clues comes from the holographic principle. In certain theories of quantum gravity, especially those described by the ADS/CFT correspondence, a gravitational spacetime in a higher dimensional region can be equivalent to a quantum theory without gravity defined on its lower dimensional boundary. The correspondence is not a speculative analogy in the loose sense. It is a precise mathematical framework with extensive evidence in particular classes of theoretical systems, though the spacetime involved is not simply the expanding universe around us. Within holographic models, entanglement in the boundary quantum theory is related to geometry in the gravitational description. The Ryu-Takayanagi formula and its extensions connect the entanglement entropy of a boundary region to the area of a particular surface in the bulk spacetime. This is an astonishing bridge. A measure of quantum correlations becomes proportional to a geometric area. Change the entanglement structure, and the associated geometry changes. This has encouraged a powerful idea. Perhaps spacetime geometry is not fundamental in the deepest theory. Perhaps some aspects of connected space emerge from patterns of quantum entanglement. The phrase entanglement builds spacetime is appealing. It must not be mistaken for an established fact about our universe. The strongest results live inside specific theoretical frameworks. ADS/CFT involves anti-de Sitter spacetime. while cosmological observations indicate that our large-scale universe is better approximated by a spacetime with positive dark energy like acceleration, not a simple anti-de Sitter background. Researchers are actively trying to understand how far holographic lessons generalize. So the careful statement is not that physicists have discovered that space is made of entanglement. It is that in some of the best developed models of quantum gravity, geometric quantities are tightly encoded in quantum entanglement, suggesting that the relationship between space and quantum information may be more fundamental than classical physics imagined. This possibility changes the emotional meaning of distance. In ordinary life, distance seems primary. Two objects are near or far because space lies between them. Their interactions weaken or take time because they must cross that distance. Entanglement suggests a second kind of relationship, one not captured by ordinary spatial separation alone. Two regions can be far apart geometrically while sharing a non-classical quantum state. In holographic settings, changing correlation structure can even change which parts of the gravitational description appear connected. This is not a hidden tunnel through which messages travel. It is a sign that the mathematical architecture of quantum theory organizes reality differently from a collection of independent points in a pre-existing container. The connection with wormholes has made the idea even more famous. A conjecture called ER equals EPR, proposed by Juan Meldacena and Leonard Susskind, suggests a relation between Einstein-Rosen bridges, a type of non-traversable wormhole, and Einstein-Podolsky-Rosen entanglement. The slogan is memorable because both sides carry Einstein's name. It does not mean that every pair of entangled laboratory photons is connected by a little usable tunnel in ordinary spacetime. It proposes that certain forms of entanglement and certain geometric connections may be two descriptions of related underlying quantum structure. In known examples, the wormhole does not allow faster than light travel. The idea is part of an active attempt to reconcile gravity and quantum information, not a confirmed picture of microscopic space. This distinction matters because entanglement attracts exaggeration. A laboratory result becomes a claim that consciousness changes reality. A Bell violation becomes proof that everything communicates instantly. A holographic calculation becomes proof that the universe is a simulation. None of those conclusions follows. The actual physics is strange enough without adding unsupported layers. What experiments show is precise. Quantum states can be entangled. Bell inequalities can be violated. Local hidden variable models satisfying the usual independence assumptions cannot reproduce those correlations. The correlations cannot be used for controllable superluminal communication. Entanglement can be generated, manipulated, distributed, lost to environmental decoherence, and used as a resource in quantum information tasks. What the experiments do not uniquely show is equally important. They do not tell us that one particle sends a secret signal to another. They do not establish a preferred frame of instantaneous influence. They do not select Copenhagen over many worlds, Bohmian mechanics, or every other interpretation. They do not prove that space-time emerges from entanglement. They do not demonstrate that human awareness causes collapse. They do not allow telepathy, teleportation of people, or communication into the past. Clarity about these limits makes the genuine result more impressive. The genuine result survived. For generations, physicists tried to replace it with a more familiar classical story. Bell showed that one broad familiar story had measurable consequences. Experiments checked. Nature crossed the boundary. There is another cosmic setting in which entanglement may matter: the early universe. According to the leading inflationary picture, the observable universe underwent an early period of accelerated expansion. Quantum fluctuations in fields were stretched to enormous scales. Those fluctuations eventually contributed to the density variations from which galaxies and large-scale structure grew. The usual calculation begins with quantum states. Modes of the fields can possess correlations and, in appropriate descriptions, entanglement. As the universe expands and interactions with unobserved degrees of freedom become important, decoherence helps classical-looking perturbations emerge from quantum origins. The tiny temperature variations mapped in the cosmic microwave background are therefore connected, through a long chain of theory and cosmic evolution, to primordial quantum fluctuations. This does not mean a telescope has performed a Bell test on the early universe. Demonstrating specifically quantum entanglement in cosmological observables is extraordinarily difficult, and much of the primordial quantum information may be inaccessible. Researchers have proposed signatures that could distinguish quantum origins more sharply, but the observational challenge is severe. Still, the possibility is profound. The seeds of galaxies may have originated in quantum fluctuations whose description involved correlations unlike anything in classical physics. A concept tested with pairs of photons on an optical table may also belong to the history of cosmic structure. Entanglement is therefore not merely small-scale physics. Quantum mechanics applies to systems regardless of size. The reason classical behavior dominates large objects is not that the laws turn off when something becomes large. It is that control becomes harder, environmental coupling becomes overwhelming, and particular quantum features become inaccessible. Experiments have pushed entanglement into larger and more complex systems over time. Collections of atoms can be entangled. Mechanical modes can be placed in non-classical correlated states. Superconducting circuits involving enormous numbers of electrons behave as controllable quantum degrees of freedom. Quantum networks entangle nodes separated by macroscopic distances. The boundary between quantum and classical is not a simple line drawn at a certain physical size. It is a question of state preparation, isolation, interaction, measurement, and information flow. This is why Schrödinger's cat remains useful despite being overused. The cat was not invented as a proposal for a real experiment involving cruelty to animals. Schrödinger wanted to expose the discomfort of extending a microscopic superposition through a measurement chain to a macroscopic outcome. If an atom can be in a quantum superposition and a mechanism couples the atom to a macroscopic event, where does the ordinary definite world enter? Entanglement is the mechanism that extends the correlation. The atom becomes entangled with the detector. The detector becomes entangled with the larger apparatus. The apparatus becomes entangled with the environment. Decoherence rapidly suppresses interference between macroscopically distinct records. What remains controversial is whether that process alone explains why one definite outcome is experienced, whether all outcomes persist in branches, whether an objective collapse occurs, or whether the question should be reframed relationally or informationally. The measurement problem and entanglement are therefore inseparable. Every measurement is, at bottom, an interaction that correlates systems. A microscopic property becomes a macroscopic record because information about it spreads into many degrees of freedom. A pointer position can be copied into photons, electronics, memory, paper, and human observers. This redundancy is one reason the classical world feels objective. Many observers can independently access records from the environment without controlling the microscopic system that produced them. Ideas such as quantum Darwinism study how certain robust states proliferate information into the environment and become effectively classical records. Again, the language is modern, but the problem is old. How does the definite everyday world arise from a quantum formalism capable of superposition and entanglement? There is no universally accepted one-sentence answer. There is, however, an increasingly detailed physical account of decoherence, information spreading, and the stability of records. The mystery has become more precise. That pattern repeats across the history of entanglement. Einstein's discomfort became EPR. EPR became Bell's theorem. Bell's theorem became experimental inequalities. Experimental inequalities became loophole-free tests. The tests became quantum information protocols. The protocols became engineering programs. And the same mathematics returned to questions about matter, black holes, and spacetime. A foundational argument did not disappear when it became technology. It widened. One way to appreciate how far the field has traveled is to follow the scale of the experiments. The earliest Bell tests were tabletop optical experiments with severe limitations in detector efficiency and switching speed. Later laboratories separated stations by meters, then kilometers. Randomness was generated fast enough to choose measurement settings while particles were already traveling. High-efficiency detectors reduced the fraction of missing events. Atomic and solid-state systems allowed entanglement to be stored rather than simply detected in flying photons. In the 2015 Delft experiment, 2 electron spins in diamond were located in separate laboratories about 1.3 kilometers apart. Each spin became entangled with a photon. The photons traveled to a station between the laboratories, where a joint measurement could herald that the remote electron spins had become entangled. Only the successful heralded events were used for the Bell test. Then the remote spins were measured with settings chosen so quickly and at such separation that the relevant events were space-like separated. The number of successful trials was small by the standards of modern data science, because generating remote spin entanglement was difficult. The statistical violation was correspondingly modest. But the architecture closed both the locality and detection loopholes in one experiment. Other teams in 2015 used entangled photons with highly efficient detectors and produced stronger statistics under different implementations. The value of multiple experiments is important. A foundational conclusion should not depend on one laboratory, one detector technology, one species of particle, or one data analysis method. Bell violations have now been observed with photons, ions, superconducting systems, solid-state spins, and other platforms under many arrangements. The details change. The non-classical boundary survives. Some experiments have turned the freedom of choice issue into an astronomical story. If a local hidden variable explanation were to exploit a correlation between the particle source and the random setting generators, perhaps that correlation arose from a common event in their past. Researchers therefore used photons from distant stars or quasars to help determine the measurement settings. The light had been traveling toward Earth for years, centuries, or billions of years depending on the experiment. Any hypothetical common cause capable of coordinating both the emitted entangled particles and the astronomical setting choices would have to reach increasingly far back into the overlap of their past light cones. This does not logically eliminate superdeterminism. A superdeterministic account can place the correlations as deep in cosmic history as necessary. But the experiment transforms a laboratory loophole into a cosmological requirement. That is a remarkable example of how seriously physicists have tested the assumptions around Bell's theorem. Another experiment invited human beings around the world to generate unpredictable bit streams from measurement choices in what became known as the Big Bell test. The point was not that human decisions are magically outside physics. It was to attack the setting independence question from a different direction and demonstrate Bell violations across multiple laboratories and physical systems with choices supplied by people rather than only electronic random number generators. These experiments also reveal an important distinction between closing an experimental loophole and closing a philosophical loophole. A detector loophole can be addressed by better detectors. A locality loophole can be addressed with distance, timing, and fast switching. The deepest assumption about whether measurement settings can ever be independent of hidden variables belongs partly to the structure of the theory itself. No apparatus can step outside the universe to prove that its own choices are metaphysically free. Science instead makes assumptions explicit and asks what follows from them. Bell's theorem is powerful because the assumptions are natural enough that their failure would itself teach us something profound. Entanglement has another property that makes it useful for security in networks: monogamy. The word sounds almost human. In quantum information, it refers to a restriction on how strongly a system can be entangled with multiple independent systems at once. If two qubits share maximal entanglement, a third system cannot be equally maximally entangled with either of them in the same way. Quantum correlations cannot be freely duplicated and shared like classical data. This is closely related to why eavesdropping can be detected and why quantum states cannot be cloned. An attacker who tries to create a perfect extra copy of an unknown quantum signal would violate the structure of the theory. Entanglement monogamy also appears in black hole information discussions, where one system may seem required to be strongly entangled with two different partners at once, producing tension among assumptions about horizons and unitarity. The same abstract constraint travels from cryptography into gravity. Entanglement can also be weak, noisy, or mixed. A laboratory state is rarely the perfect Bell pair drawn in a textbook. Photon loss, imperfect gates, detector noise, thermal populations, and phase drift reduce its quality. Scientists therefore need ways to determine whether a state is genuinely entangled without reconstructing every detail. An entanglement witness is one such tool. It is an observable designed so that every separable state obeys a certain bound. If the measured value crosses that bound, entanglement is certified. For small systems, full quantum state tomography can reconstruct the density matrix from many measurements in different bases. For large systems, full tomography becomes impractical because the number of parameters grows rapidly. Researchers instead use witnesses, randomized measurements, correlation functions, entropy estimates, and structure-specific methods. Again, the story becomes statistical. Entanglement is not visible as a glowing line between objects. It is inferred from patterns of measurement outcomes that cannot be reproduced by separable states under the assumptions of the analysis. This matters when laboratories try to distribute entanglement through a network. Suppose a photon carrying half of an entangled pair passes through kilometers of fiber. Most photons may be lost before reaching the detector. Those that survive may suffer polarization rotation, phase noise, or timing uncertainty. If the remaining pair is too noisy, its entanglement may be unusable. Entanglement purification offers one response. Given several imperfect entangled pairs, local operations and classical communication can sometimes sacrifice some pairs to produce fewer pairs with higher fidelity. The procedure cannot create entanglement from purely separable states using local operations alone. It concentrates a resource already present. This fact is formalized in resource theories of entanglement. The basic rule is that if Alice and Bob are far apart and restricted to local operations plus classical communication, they cannot manufacture entanglement between their laboratories from nothing. They need a quantum channel, previously shared entanglement, or a physical process that distributes quantum systems between them. Once they have it, they can transform one pattern into another under precise constraints. This resource perspective gives entanglement a kind of accounting system. How much is present? How much can be distilled? How much is required to perform a task? Which transformations are possible without sending additional quantum systems? These questions sound very different from Einstein's original objection, yet they descend directly from the same non-separability. A Bell pair becomes a unit of shared quantum correlation. A useful thought experiment is to imagine that Alice and Bob share 1,000 perfect Bell pairs, but no communication channel at all. Can Alice tell Bob that it is raining? No. She can measure her particles in any pattern she wants. Bob sees random local outcomes. Can they perform teleportation? Not completely. Alice can perform the joint measurements, but Bob will not know which correction to apply until the classical bits arrive. Can they create correlated random strings? Yes, if they agree in advance on compatible measurements. But Bob still cannot know whether Alice actually measured until ordinary information reaches him. This thought experiment separates connection from communication. Entanglement is a resource, but not a message. The distinction is so important because many popular explanations accidentally erase it. When a measurement is made on one particle, the conditional predictions for the other change. If Alice reports that she obtained a particular result, Bob can immediately update what he predicts for his corresponding measurement. But Bob cannot observe Alice's update from his laboratory before her report arrives. The conditional state and the locally observable state are not the same thing. This is the operational core of no signaling. It is also why quantum teleportation does not violate causality. Bob's particle may be described conditionally as one of several states after Alice's measurement. From Bob's isolated perspective, before receiving Alice's classical bits, those alternatives average to a state that contains no usable information about the unknown input. The classical message unlocks the correlation. No light speed limit has been bypassed. Delayed choice entanglement swapping experiments push intuition further. In some arrangements, measurements can be ordered so that the decision about how to measure intermediate particles occurs after other particles have already been detected. When the data are later sorted according to the intermediate measurement outcomes, subsets display entangled or separable correlations. This can sound as if a later choice rewrites whether earlier particles were entangled. That is not what an observer can see in real time. The earlier local records are already fixed and show no usable retrocausal signal. The later measurement determines how joint data are conditioned and which correlations become visible when records are compared. These experiments are valuable because they force classical narrative habits to fail. They do not provide a machine for changing the past. Quantum theory often resists a single story in which every system carries a complete set of properties through time independent of all measurement context. The mathematics predicts joint probabilities more reliably than the classical movie we try to place behind them. This is why the phrase strangest connection in the universe should not be understood as a literal chord. The connection is a failure of separability. The state of the whole contains structure that no assignment of independent local states can reproduce. Bell experiments add another layer. For suitable entangled states, that structure cannot be explained by local hidden variables of the familiar kind. Distance does not erase it. Noise can. Interaction with the environment can. Poor preparation can. Loss can make it inaccessible. But geometric separation by itself is not what ends entanglement. Two photons do not have to remain close to stay entangled. They have to avoid interactions that destroy or redistribute the relevant coherence. This distinction points toward the largest entanglement experiments imaginable. A satellite can send photons to widely separated ground stations. A future repeater network could entangle quantum memories across cities or continents. In principle, quantum systems separated by astronomical distances can remain entangled if coherence can be preserved and the protocol can overcome loss. The limiting difficulty is engineering, not a quantum rule saying entanglement expires after a certain number of kilometers. That is why distance in entanglement feels paradoxical. The correlations are independent of an ordinary travel time once the entangled state is established and the measurements are space-like separated. Yet creating, distributing, verifying, and using that state always takes physical processes inside spacetime. The pair has a history. The photons came from a source, or the distant memories became entangled through intermediate photons and heralding measurements. Classical messages are needed to coordinate protocols and compare results. Entanglement does not erase causality from the universe. It inserts non-classical correlation into a causal universe. There is one more surprising boundary hidden inside Bell's theorem. Quantum correlations are stronger than local classical correlations, but they are not as strong as mathematics alone would allow if the only rule were no faster than light signaling. This is easiest to see in the CHSH form of a Bell test. A local hidden variable model obeys a classical bound. Quantum mechanics can exceed it. Yet quantum mechanics stops at another value, known as Tsirelson's bound. One can imagine hypothetical correlations that violate the Bell inequality even more strongly, while still preventing either observer from sending a controllable signal to the other. A famous mathematical example is called APR box, after Sandu Popescu and Daniel Roerlich. APR box is not known to exist in nature. It is a thought experiment, a device with correlations stronger than quantum entanglement, arranged so that Alice's local outputs remain random and Bob's local outputs remain random. No message can be sent. Yet when their outputs are compared, the joint pattern beats the strongest correlation permitted by quantum mechanics. This raises a question that Bell's theorem alone does not answer. Why is nature quantum rather than even more non-local? Why does the universe stop at Tsirelson's bound? Researchers have explored principles that might single out quantum correlations from the larger space of mathematically possible no-signaling correlations. One idea is information causality. Even with arbitrary shared resources, sending a limited amount of classical information should limit how much useful information a distant observer can gain about an independent data set. Other proposed principles involve local orthogonality, macroscopic locality, computational complexity, and the internal consistency of probabilistic theories. The program asks whether quantum mechanics can be reconstructed from simple information theoretic or operational principles rather than taken as a mysterious list of mathematical rules. This is a modern version of a very old scientific ambition. Einstein wanted to understand why the structure of relativity followed from principles about light and inertial motion. Thermodynamics can be developed from constraints on heat and work. Perhaps quantum theory can be understood as the unique theory that allows non-classical correlations while preserving deeper constraints on information and causality. No single reconstruction has settled every foundational question, but the effort reveals something important. Entanglement is not equivalent to unlimited non-locality. Quantum theory occupies a particular region between classical locality and the broadest no-signaling possibilities. Nature violates Bell inequalities, but only in a disciplined quantum way. That discipline is another clue. It tells us that the universe has not simply abandoned causal structure. The correlations are constrained by a mathematical architecture that remains compatible with relativistic communication limits. The word spooky can make quantum mechanics sound anarchic. It is almost the opposite. The theory is strange because its rules are rigid. The same amplitudes that create Bell violations also imposed Tsirelson's bound. The same entanglement that powers teleportation also obeys monogamy. The same no-cloning theorem that complicates quantum networking helps make quantum cryptography possible. The same measurement disturbance that threatens computation can be turned into an error syndrome without revealing the logical state. Quantum information is a web of constraints. Its power comes from the shape of those constraints, not from the absence of rules. This becomes easier to appreciate when entanglement is no longer restricted to carefully prepared pairs. Ordinary matter is quantum matter. An atom is not built from classical particles orbiting like planets. Its electrons occupy quantum states shaped by the electromagnetic interaction, the Pauli exclusion principle, and correlations with other particles. In molecules, electrons can become correlated across chemical bonds. In solids, Enormous numbers of electrons and atomic spins can participate in collective quantum states. Not every useful quantum correlation is entanglement in the same technical sense, and not every material at room temperature contains entanglement that is easy to isolate or exploit. But entanglement is woven into the modern description of many physical systems. Consider two spins inside a magnetic material. At high temperature, thermal agitation may dominate, and the state can become well approximated by a classical mixture for many purposes. Cool the system, strengthen particular interactions, or approach a quantum critical point, and entanglement can become essential to describing the ground state. The system may develop correlations that persist over long distances or encode global topological structure. Temperature creates an interesting competition. Quantum interactions build entanglement. Thermal mixing tends to wash out the coherent structure needed to observe it. There is no universal temperature above which all entanglement disappears. The answer depends on the system, interaction strengths, degrees of freedom, and the partition being studied. Some forms of entanglement can survive surprisingly warm conditions in strongly interacting systems. Others vanish with tiny amounts of noise. This is why a quantum computer may require millikelvin refrigeration, while certain biological molecules still obey quantum chemistry perfectly at room temperature. Quantum behavior itself is not synonymous with fragile macroscopic entanglement. The laws are universal. The controllable resource is fragile. A chemical bond does not become classical because a laboratory is warm. But preparing hundreds of engineered qubits in a precise, coherent many-body state and keeping that state useful for computation is a far more demanding task. The distinction also helps with another popular question. Are the particles in a human body entangled? Interactions continually create quantum correlations. In that broad sense, entanglement appears and spreads throughout matter. But a warm biological system is strongly coupled to its environment. Photons, molecular collisions, vibrations, chemical reactions, and thermal motion rapidly redistribute phase information into an enormous number of degrees of freedom. One should not picture each atom carrying a clean, invisible partner connection left over from the early universe. The state of a macroscopic organism is vastly more complicated. Useful isolated Bell pairs do not survive casually through billions of uncontrolled interactions. The quantum description remains fundamental, but the specific entanglement structure is continually changing. This gives decoherence a more concrete meaning. Suppose a qubit begins entangled only with a second qubit in a laboratory. Then an environmental photon scatters from the first qubit in a way that depends slightly on its state. Now the photon carries some information about the qubit. The original pair is no longer a closed system. Another photon scatters. A nearby atom interacts. A cable mode absorbs energy. The controlled correlation becomes shared with a growing environment. From the experimenter's perspective, the two-qubit state loses purity and fidelity. The environment has not necessarily erased quantum mechanics. It has taken part in it. This is why isolation and error correction are complementary strategies. Isolation tries to prevent unwanted entanglement. Error correction accepts that some unwanted interactions will happen and encodes the information so their effects can be detected and reversed before they accumulate beyond repair. In a quantum network, purification plays a similar role. In a quantum sensor, carefully chosen entanglement may increase precision, while uncontrolled environmental entanglement creates noise. Across technologies, the problem is never simply more entanglement is better. The problem is the right entanglement with the right systems at the right time. That sentence captures much of quantum engineering. It also explains why entanglement should not be treated as a mystical universal glue. Gravity holds masses in orbits. Electromagnetism binds atoms and molecules. The nuclear interactions shape atomic nuclei. Entanglement is not another force added to that list. It does not pull two objects together. It does not supply energy merely because two systems are correlated. It describes a property of the quantum state generated by interactions and preparation processes. Two distant entangled photons do not accelerate toward each other because of entanglement. Two entangled qubits do not remain connected because a new field stretches between them. The connection is informational and structural in the quantum state, while the physical systems still obey the ordinary dynamics of the interactions acting on them. This distinction becomes especially important in popular discussions of wormholes. If entanglement and geometry are related in a future theory of quantum gravity, that would not transform entanglement into a fifth force. It would suggest that our concepts of geometry and quantum information share a deeper origin. The difference is enormous. One is a claim about a new interaction. The other is a claim about what the stage called spacetime may ultimately be. The strongest version remains open. What is already established is enough to be remarkable without it. Laboratories can create a state whose parts have no separate pure descriptions. They can separate those parts. They can choose incompatible measurements at space-like separation. They can observe correlations that violate Bell inequalities. They can use entanglement in teleportation and cryptographic protocols. They can encode quantum information into many body entangled states and begin correcting errors in real time. And they can quantify entanglement in materials whose collective behavior would be difficult to understand without it. The phenomenon has moved from philosophical challenge to experimental fact to practical resource. It has also become a diagnostic tool for theory itself. If a proposed model of matter, computation, or gravity predicts the wrong entanglement structure, that failure can reveal that the model is missing something essential. Entanglement is therefore not only something systems possess. It is something physicists use to interrogate the architecture of a theory. In condensed matter, entanglement reveals hidden order. In quantum information, it measures resources and limitations. In black hole physics, it tracks information across horizons and radiation. In holography, it is tied to geometric surfaces. In Bell tests, it exposes the failure of local hidden variable explanations. One concept passes through all of these subjects because all of them ask, in different language, how the state of a whole is distributed among its parts. Between ordinary entanglement and a full Bell violation lies another idea that grew directly from the EP/R debate: quantum steering. Schrödinger introduced the term after reading the Einstein-Podolsky-Rosen argument. Imagine Alice and Bob share an entangled state. Bob does not trust Alice's measurement device. Alice claims that by choosing different measurements on her subsystem, she can prepare different ensembles of conditional states for Bob's subsystem. From Bob's perspective alone, before learning Alice's outcome, his local density matrix does not change. No message appears. But after Alice reports which measurement she performed and which results she obtained, Bob can sort his data into conditional groups. Those groups may be inconsistent with any model in which Bob's system carried a pre-existing local quantum state, while Alice merely revealed classical information about it. When that happens, Alice is said to steer Bob's state. Steering occupies a useful middle ground. Every Bell non-local state is entangled, but not every entangled state violates a given Bell inequality under ordinary measurements. Likewise, steering tests have their own hierarchy of assumptions and can reveal non-classicality in situations where a full device-independent Bell test may be too demanding. This hierarchy prevents the word entangled from becoming too vague. Entanglement itself means non-separability of the state. Steering asks whether correlations defeat a particular local hidden state model when one side's devices are trusted and the others are not. Bell non-locality asks whether the joint statistics defeat a local hidden variable model without trusting the internal operation of either measurement device under the relevant experimental assumptions. The concepts overlap, but they are not identical. This matters in real laboratories because different tasks require different kinds of certification. A quantum computer may need highly faithful entangling gates without performing a loophole-free Bell test between every pair of qubits. A quantum network may certify entanglement between nodes using witnesses or tomography. A one-sided device-independent protocol may use steering. A fully device-independent protocol may demand Bell violation. The stronger the conclusion, the more demanding the experiment. The distinction also corrects another popular image. Suppose two spin particles are prepared in a singlet state, and Alice measures spin along a vertical axis. She obtains one outcome. If Bob measures along the same axis, his result will be perfectly anti-correlated in the ideal state. It is easy to narrate this by saying Alice's measurement forced Bob's particle to flip into the opposite state. But that narrative imports more than the data require. Before Alice's result is communicated, Bob's local statistics are exactly what quantum theory predicted before her measurement. If Bob chooses another axis, the correlation changes according to the angle between the measurement settings. If Alice and Bob are space-like separated, different reference frames can reverse the time order of the two measurements. So physics does not provide an observer-independent movie in which Alice acts first and Bob reacts second. What is observer-independent is the joint probability distribution predicted for their settings and outcomes. This is a useful discipline in quantum foundations. When the mathematics predicts relationships more clearly than it predicts a unique underlying sequence of hidden events, the safest narration follows the relationships. The word correlation can sound weak, as though it merely describes bookkeeping after the fact. Bell correlations are not weak. They are strong enough to rule out an entire natural class of local explanations. But they are still correlations rather than observable superluminal commands. That balance is the heart of the subject. The same balance appears in conservation laws. If a source creates two particles with total angular momentum zero, conservation strongly constrains their joint state. But conservation alone does not explain Bell violation. A classical source can also emit opposite angular momenta and preserve total angular momentum perfectly. The quantum difference appears when measurements are made along several incompatible directions and the entire pattern of correlations is compared. No single same-axis anti-correlation proves entanglement's deepest feature. The rotated settings do the work. This is why Bell experiments require choice. If Alice and Bob always measured along one fixed axis, a simple local instruction could imitate the results. The source could send one particle carrying one value and the other carrying the opposite value. Once multiple settings are chosen independently and laid, the hypothetical instruction table must answer several mutually constraining questions. Bell's inequality captures the fact that no local table can satisfy them, as well as quantum mechanics predicts. The experiment turns counterfactual possibilities into a statistical boundary without ever measuring incompatible observables on the same individual particle. That last point is subtle. Alice never measures both of her possible settings on one photon in the same trial. Bob never does either. Each run uses one choice on each side. The inequality emerges across an ensemble of many runs under the assumption that a local hidden variable model would assign a consistent response structure to all possible settings. Quantum mechanics refuses to be compressed into that structure. So the strangeness is not located in one dramatic click. It is distributed across the logic of many possible measurements and many actual trials. That may be why entanglement took so long to move from philosophical discomfort to experimental fact. The crucial evidence is not a spectacle. It is a pattern that only appears after careful comparison. One more conceptual trap is worth removing before the different threads are brought together. People often ask what exactly is traveling between entangled particles. The question assumes that the correlation must be carried by something moving through the space between them at the moment of measurement. Bell's theorem is one reason that assumption becomes uncomfortable. If the explanation is a local carrier moving no faster than light after the measurement setting is chosen, appropriately arranged experiments leave no time for it to coordinate the outcomes. If the explanation is a pre-written local instruction carried from the source, Bell inequalities constrain the correlations more strongly than nature obeys. One can respond by accepting non-local variables, by rejecting measurement independence, by changing the ontology of outcomes, by adopting branching, by using relational or informational interpretations, or by exploring deeper theories. But the ordinary picture of a signal flying from A to B is not what the experiments reveal. Sometimes the best answer to what travels is, that may be the wrong category of question. The state describes the pair. The correlation is not necessarily a thing located halfway between the particles waiting to move. This is similar, though not identical, to other places in physics where a familiar noun stops fitting. What travels in a standing wave when the pattern remains fixed? Where exactly is the information represented by a parity bit distributed across a classical code word? Which individual molecule contains the temperature of a gas? Some properties belong to relations or collective structures rather than to one localized object. Entanglement is a quantum version of that lesson, made far more radical by Bell violation. Another common question asks when two particles become entangled. There is no single universal mechanism. Interaction can entangle them directly. Conservation laws can entangled entangled decay products. A joint measurement can project distant systems into an entangled state. Photons emitted in an atomic cascade can share entanglement. Two qubits in a processor can be entangled by a controlled gate. Two atoms can become entangled through photons they emit into a common optical system. Quantum statistics can also generate correlations among indistinguishable particles, though the relationship between exchange correlations and operationally useful entanglement requires careful definitions. What all these cases share is that the final state cannot be represented as an independent product of subsystem states across the chosen division. The chosen division matters too. A state may be entangled with respect to one partition of a system and not another. This is especially important in field theory and many-body physics, where deciding what counts as subsystem A and subsystem B can involve spatial regions, modes, particles, internal degrees of freedom, or combinations of them. The popular phrase two particles are entangled therefore describes the simplest case, not the full concept. Entire collections can be genuinely multipartite entangled. Three qubits can share a GHZ state in which the correlations disappear in a dramatic way if one qubit is measured or lost. Another three-qubit structure, the W state, distributes entanglement differently and can retain pairwise entanglement after one subsystem is removed. With many particles, there are numerous inequivalent patterns of entanglement. The structure begins to resemble a network more than a pair. This matters for quantum computing because algorithms build complex many-qubit states. It matters for quantum sensing because carefully engineered multipartite entanglement can improve measurement precision under certain conditions. It matters for condensed matter because phases can be distinguished by how entanglement is organized across the system. And it matters for gravity because holographic geometry seems to know about patterns of entanglement across many degrees of freedom, not merely isolated pairs. The pair is the doorway. The real landscape is many-body. Quantum sensing provides another practical example. Measurement precision is limited by noise and by the statistical nature of quantum measurements. Independent particles used as probes produce one scaling of uncertainty. Entangled probes can, in ideal circumstances, reach stronger scaling for estimating phases, fields, times, or other parameters. Atomic clocks, magnetometers, interferometers, and distributed sensors can use squeezing and entanglement-related resources to reduce quantum noise. The advantage is not automatic. Entangled states are fragile, and losses can erase the gain. But the principle is important. Correlations forbidden to classical independent probes can become metrological resources. This connects entanglement to the practical act of measuring the universe more accurately. A phenomenon once introduced through a paradox becomes a way to build better instruments. The transformation from paradox to tool may be one of the most revealing stories in modern science. In the 1930s, entanglement appeared inside an argument about whether quantum mechanics could be complete. In the 1960s, Bell found a way to turn part of that argument into a quantitative test. In the decades that followed, increasingly careful experiments showed that the correlations of entangled systems do not fit the local hidden instruction picture Bell had constrained. Then something unexpected happened. The same feature that had looked like a philosophical embarrassment became a resource. Entanglement could help teleport an unknown quantum state from one laboratory system to another, provided classical information was also sent. It could help distribute secret keys. It could connect remote quantum memories. It could improve selected sensing protocols. It could help encode information across many physical qubits so that errors in individual components did not immediately destroy the logical state. The mystery became useful without first becoming ordinary. That is worth noticing. Technology usually gives the impression that understanding must be complete before engineering can begin. Quantum physics does not always work that way. A laboratory can prepare an entangled state with great reliability while physicists continue to disagree about what the wave function ultimately represents. A quantum processor can perform an entangling gate without choosing between collapse, branching worlds, hidden trajectories, relational descriptions, or other interpretations. Operational knowledge can become precise before ontology becomes unanimous. This is not unique to quantum mechanics. People used thermodynamics before they agreed on the microscopic nature of heat. Engineers used electricity before the electron was understood. Celestial mechanics worked before gravity had a relativistic description. But entanglement makes the separation unusually vivid because the operational predictions are so exact, while the underlying picture remains so contested. That contrast is easier to appreciate if the familiar slogans are removed. Entanglement does not mean that two particles send secret messages to each other. It does not mean that distance has ceased to exist. It does not mean causality has failed. It does not mean every object that has ever touched another object remains forever joined in one pristine, usable Bell pair. And it certainly does not provide a physical mechanism through which thoughts, intentions, or emotions can act instantaneously on distant matter. Real entangled systems interact with environments. Their correlations spread into additional degrees of freedom. Phases become difficult to control. Information that was once concentrated in a simple two-system state becomes distributed through a much larger quantum state. For practical purposes, the clean entanglement can disappear extraordinarily quickly. This is decoherence again, but seen from the perspective of relationships. The quantum connection has not turned into a classical signal. The controlled correlation has become entangled with too many other things to remain accessible in the simple form the experiment required. That is why laboratories work so hard to isolate qubits. A cryostat does not protect a superconducting circuit from quantum mechanics. It protects the intended quantum state from uncontrolled quantum mechanics happening everywhere around it. Vacuum chambers, magnetic shielding, vibration control, carefully shaped laser pulses, Purified materials, error correction codes, and rapid measurements all serve the same broad purpose. They keep the desired pattern of relationships from leaking into the environment before it can be used. The fragility makes the phenomenon more, not less, interesting. Entanglement is not a decorative philosophical property added to an otherwise classical world. It is something that must be engineered, preserved, verified, consumed, swapped, purified, or protected. Its behavior has consequences, and yet the central experimental picture remains almost strangely quiet. Imagine Alice and Bob again. They are far apart. A source prepares pairs of systems and sends one member of each pair to Alice and the other to Bob. For every trial, Alice chooses one measurement setting. Bob independently chooses another. Each receives one result. If Alice looks only at her own list, she sees randomness. If Bob looks only at his own list, he sees randomness. Nothing in Alice's local data tells her which setting Bob selected. Nothing in Bob's local data tells him which setting Alice selected. There is no readable pulse traveling through the gap. There is no controllable faster-than-light message. Only later do they compare the records through an ordinary communication channel. Then structure appears. The correlation between their outcomes depends on the pair of measurement settings. Across many trials, the pattern can violate a Bell inequality. That violation is the crucial part. Simple correlation is not enough. Two classical objects can be correlated because of a common past. Two envelopes can contain matching instructions. Two gloves can be placed in separate boxes. A pair of clocks can be synchronized before separation. None of those examples is mysterious. Bell's theorem asks whether a much broader class of local pre-written explanations can reproduce all the correlations predicted by quantum theory when Alice and Bob are free to choose among different measurement settings. Under the standard assumptions of the test, the answer is no. Experiments agree with the quantum prediction. That is where the strangeness lives. Not in one detector click. Not in one distant coincidence. Not in the fact that measuring one member of a correlated pair teaches us something about another. The strangeness lies in the entire statistical pattern across alternative measurement choices. Nature behaves as though the complete classical description cannot be assembled from independent local properties carried by the two systems from the source. This statement is strong. It is also narrower than many popular descriptions. Bell tests do not eliminate every imaginable hidden variable theory. Bohmian mechanics, for example, keeps hidden variables while being explicitly non-local. Superdeterministic approaches question the independence assumptions used in Bell reasoning. Retrocausal approaches explore whether future measurement choices can be part of a time-symmetric explanation of earlier hidden structure. Different interpretations change which classical intuition they are willing to abandon. Bell's achievement was not to force all physicists into one ontology. It was to show that certain attractive assumptions cannot all survive together if the experimental predictions of quantum mechanics are correct. The experiments then made that tension physical. This is why the phrase local realism can be useful but also dangerous. It compresses several ideas into two words. Locality can refer to restrictions on influences or causal structure. Realism can refer to pre-existing values, observer-independent properties, hidden variables, or stronger philosophical claims. Different Bell theorems and interpretations formulate these assumptions in different ways. For a careful understanding, it is better to say exactly what the experiment constrains than to announce that reality itself has been disproved. Reality has not been disproved. A particular classical style of explaining separated systems has failed. Relativity survives alongside this failure. That coexistence is one of the most subtle features of modern physics. Special relativity says that controllable influences cannot be used to transmit information outside the light cone. Quantum mechanics respects that operational limit. Bell correlations nevertheless cannot be reproduced by the relevant local hidden variable models. The result is a theory with non-classical correlations and no superluminal communication. Those two facts are not contradictory. They are part of the same experimentally successful framework. This also clarifies the phrase action at a distance. If the phrase suggests a force leaving Alice's laboratory, crossing space instantaneously, and striking Bob's particle, it is a poor description of what has been observed. No such traveling agent has been detected. Some interpretations introduce non-local structure. Others avoid describing a physical collapse traveling through space. Many worlds keeps unitary evolution and places the correlations in the branching structure of the global wave function. Relational and informational approaches frame the state differently again. The experimental data alone do not show a tiny courier racing faster than light. They show correlations. That difference sounds restrained, but it leaves a deeper question. What is a physical system if the most complete state cannot always be assigned separately to its parts? In an entangled pair, each subsystem can have a perfectly well-defined reduced quantum state, while the joint system contains additional information in the correlations. Knowing the local states does not necessarily tell you the global state. The whole possesses structure that is not stored inside either part by itself. This idea becomes richer in many body systems. With 3 particles, there are already inequivalent ways of sharing entanglement. With hundreds or millions, the pattern can distinguish phases of matter, constrain simulations, influence transport, and reveal collective organization. In quantum error correction, logical information can be encoded into relationships among many physical qubits so that no single component carries the full logical state. In quantum networks, entanglement can be extended through swapping operations even when the end systems never directly interacted. In quantum gravity research, patterns of entanglement appear in mathematical relationships between quantum information and geometry. None of this proves that the universe is literally woven from invisible quantum threads. It does show that relationships can be as fundamental to the calculation as the individual objects being related. That may be the most useful way to understand the word connection in quantum entanglement. Not as a cable, not as a force, not as communication, as a property of a joint quantum state that cannot be reduced to independent descriptions of its pieces. Distance does not automatically erase that property. Interaction with the environment often does. This distinction matters. 2 systems can become separated by kilometers while a carefully protected entangled state remains measurable. 2 systems separated by a microscopic distance can lose useful entanglement almost immediately if they interact strongly with uncontrolled surroundings. Physical distance and quantum independence are not the same concept. This is one reason entanglement enters modern discussions of spacetime. Classically, space encourages a picture of independent objects occupying different places. Quantum theory allows systems in different places to belong to one non-separable state. Holographic models go further and connect certain measures of entanglement to geometric quantities. Those ideas are mathematically deep and potentially important for quantum gravity. But they should be allowed to remain what they are: research programs and theoretical relationships, not evidence that ordinary space has already been derived from entanglement in our universe. The distinction between established result and ambitious possibility runs through the entire subject. Established, entangled states are routinely created. Established, their correlations can violate Bell inequalities. Established, loophole-free experiments have strongly tested the relevant local explanations. Established, entanglement can be used as a resource in quantum information protocols. Established, those protocols do not permit controllable faster-than-light signaling. Open, which interpretation gives the best account of measurement? Open, whether the wave function should be regarded as a physical object, information, a relation, or something else. Open, whether deeper physics will eventually modify quantum mechanics. Open, how quantum information, gravity, and spacetime fit together in a complete theory. Keeping those categories separate does not make the subject less strange. It makes the strangeness more durable. A mystery built from exaggeration disappears when the exaggeration is corrected. Entanglement remains remarkable after correction. That is the stronger kind of mystery. Einstein's objection deserves the same care. He was not simply an old physicist unable to accept new ideas. He had helped build quantum theory. He understood its mathematical success. His concern was that a satisfactory physical theory should describe separated systems with a kind of independent reality that the quantum formalism seemed to deny. The EP argument sharpened that concern. Bell later discovered that a local hidden variable completion of the relevant kind would obey statistical limits. Nature violated those limits. So Einstein's preferred route back to a local classical picture did not survive. But the question he emphasized was real. What does it mean for distant systems to possess physical properties independently? Quantum theory still forces that question into uncomfortable territory. Bohr answered in one language. Everett answered in another. Bowman another. Modern interpretations continue the disagreement. The laboratory does not settle all of it. The laboratory settles the correlations. And perhaps that is enough for the final return to the experiment. Alice and Bob stand apart. Their apparatus is quiet. One detector registers a result. Another detector registers a result. Neither record, by itself, contains a message from the other side. Neither observer sees anything supernatural. The lists grow. Hundreds of trials. Thousands. Millions in some implementations. Settings are chosen. Outcomes accumulate. Only when the records are compared does the hidden shape of the experiment appear. The numbers cross the classical boundary. A local instruction book cannot reproduce the pattern under the assumptions being tested. No flash crosses the room. No particle announces that reality has become non-local. There is only a statistical result. And behind that quiet result lies one of the deepest revisions physics has ever made to the idea of separateness. The universe still has distance. Light still requires time to cross it. Causality still constrains communication. A star 1,000 light-years away remains 1,000 years away by light signal. Entanglement does not shorten the journey. What it changes is the assumption that spatial separation automatically means complete physical independence. Quantum systems can share a state whose information belongs to the relation between them. That relation can survive separation. It can be measured. It can be engineered. It can be lost. It can be used. And in Bell experiments, it can produce correlations that a natural family of local classical explanations cannot match. That is enough. No whispering particles are required. No faster-than-light message is required. No supernatural thread is required. The measured connection is stranger because it is quieter than those images. It sits inside probabilities. It appears only when distant records are brought together. It preserves the causal limits of relativity while refusing the simple classical picture of independent pre-existing answers. Quantum entanglement began as a reason to doubt whether quantum mechanics could possibly be complete. It became a theorem, then an experiment, then a laboratory resource. Now it reaches into computation, communication, sensing, condensed matter, and some of the deepest attempts to understand spacetime. Yet at its center is still the same small surprise. The most complete description of two quantum systems may belong to the pair before it belongs to either one alone. The correlations are real. The no-signaling limit is real. The violation of Bell inequalities is real. The technologies built from entanglement are real. The final ontology beneath those facts remains open. And that is a good place to leave the strangest connection in the universe. Not as two particles talking across the dark, as two distant measurements, locally random and causally silent, revealing a shared quantum structure only when their histories are brought together. A universe in which distance matters. A universe in which relationships matter too. Good night.